On the right, I've shown what are called the Voronoi or Dirichlet cells that take that associate to every point all the points of space that are closer to that point than to any other point. And the dual decomposition is the Delaunay triangulation. And what was used in the proof of the Kepler conjecture was a hybrid decomposition that combined the two. So you see some triangles and some of the Voronoi cells overlapping with them. You can show a proof theorem showing that these two decompositions cannot work. You're really forced to use something more complicated. So another thing that I did was in 2009, I organized an international workshop in Hanoi. It ran for 2 months, and we taught functional programming, we taught discrete geometry background, we taught formal proof methods, and half the collaborators for the final project came out of this group. So this was the real turning point in drawing from something that seemed quite overwhelming to me to something that had a big team behind it and a lot of momentum. So this is the announcement of the solutions, the completion. So this project is now complete, finished in August of last year. The original intention was to do this all in the whole light proof assistant very early on. So B.S. Nimco and Gertrude Bauer became involved in Munich, and Nimco was involved in the, he's one of the architects of the Isabel system. And so I could hardly ask the architect of a proof assistant not to use his own system in his work. And so he did one piece of the formal proof of the Kepler conjecture inside the Isabel proof assistant. And so what we do, the logics of the two systems are very closely related, but what we do is we just take the statement that he proves and translate that verbatim into the whole light system, and then we introduce that as an assumption. So our actual final result is still spread between two different proof assistants. One statement in Isabel and everything else in whole light. So this is what it looks like in the whole light system. We define a packing in terms of the centers of the balls. And if we normalize the radius of each ball to be 1, then the centers have distance at least 2 from each other. This is all done with a ASCII character set. So universal quantifiers, for instance, are done with exclamation points. So some of this looks a little bit strange. This is conjunction, if and only if, implication, and so forth. This ampersand, so whole light makes a distinction between natural numbers and real numbers. And so this is the embedding of natural numbers into the real numbers. So it's a little bit ugly to have this extra symbol, but this is 2 read as a real number. And then here's the statement of the Kepler conjecture. It says for every packing, there exists a constant used in the error term, such that for every R, what we do is we consider a packing inside some finite container and count the number of sphere centers, and then what we get is this number that I showed in an earlier slide, pi over the square root of 18, plus an error term, and this error term divided by the volume of the container goes to 0 as the radius. So we take R to infinity, and we get pi over 18. So this is what we formalize inside the system. And then when you have a formal proof, you want to know that you actually formalize the right theorem. And so you need to check not just the statement, but you need to look to audit the proof. You need to look at all the definitions going back to make sure that there's no cheating going on. That, if I were to find pi to be some really big number, then it'd be easy to prove that the density is always less than pi over square root of 18, right? So here you check that pi really does have a property that uniquely characterizes the number. And here, so you want to do the same with, you want to show that there's no cheating with other terms like the metric that you're using, or what finite sums are, how you define the square root, and so forth. So with a formal proof, there is a little bit of checking that has to be done by the human who understands mathematics. And that is, you really need to see that the definitions correspond to what it is that you want to be formalizing. So in the original proof and in the revised proof, there are three main bodies of computer code. One I've already described, there are about 1,000 inequalities that come up. And so now we need to think about how to do the computer parts of the proof formally. So I described how we did things in the original proof, how we used inequalities, we used interval arithmetic, and used Taylor expansions using automatic differentiation and so forth. So we don't want to formally prove 1,000 inequalities now by hand, going all the way back to the foundations. This would be an incredible amount of work. And like I said, this took about 3 months back in 1998, and we've had Moore's Law speed things up since then. But from the very beginning, it was pretty clear that this was going to be the biggest challenge of the project, to prove all of these inequalities in a completely automated and formal way inside the proof of system. And this was done by Solovyov in his thesis. And so what he does is he implements all of those algorithms inside the proof of system. So floating point numbers are created inside, completely inside the proof of system, inside the logic. The automatic differentiation routines are all put in the Taylor series and so forth. And automatic procedures are created that justify all of the steps of the algorithms of the computer. So the rough guide that we found is that in going from just an ordinary floating point calculation in the computer to doing something that's formally verified slows things down by a factor of about 2,000. That's just the way the technology is right now. And we started with a 3-month calculation. You see, we've got a bit of a problem. Now, so just reworking the code and using Moore's Law, we were eventually able to get this down to a 10-hour calculation just using ordinary floating point. So a factor of 2,000 now gives us a 20,000-hour calculation that we needed to do inside the proof of system. In the end, we were able to get it down to a 5,000-hour calculation, and so that's what was finally done. So to do the formal verification of the Kepler conjecture, it takes about 5,000 hours of cloud computing, and almost all of that goes into these proving of these nonlinear inequalities that go into the proof. The main part of the text can all be checked in about 300 pages of text. That goes through in about 5 hours. So that's really not the problem. The problem is really, from the start, dealing with these nonlinear inequalities. So there was one problem that comes up with this, and that is that the way whole light is designed, every time you start out the session in whole light, it starts all the way at the foundations of mathematics, and it reproves everything, it does all the calculus and, construction of natural numbers and the whole thing, justifying everything as it loads. So nothing is saved out, no theorems are saved out to disk. Every time you go, it reproves everything from scratch. But during a cloud computation, it really wasn't feasible for us to do this all inside a single session of whole life. We really had to do this on different computers and combine them. So what we did is we broke this up into 23,000 pieces, farmed it out on the cloud, and then we made one specially modified version of whole light that it checks. So the meaning of the theorem is determined by all of the constants that appear in the theorem, and the definitions of all those constants, and then recursively back to how those constants are defined. And similarly with the types, you have types, and those types depend on other types. And so every theorem has a whole history that determines its meaning. And in this special session of whole light, we allowed the import of the theorem if the entire history of the two terms agree, and it's been proved in one system, we allowed it to be imported into this special master version of whole light. And in that way we're able to combine all of the nonlinear inequalities. And so what we get in a single session of whole light is this implication that if we import this one result from Isabel that was done in this other system, and if we assume the nonlinear inequalities, then we get the Kepler conjecture. So, and then we have separate sessions that give, this is a specially modified session, gives all the nonlinear inequalities, and then we have this direct translation of this one statement from Isabel. And so we have two assumptions here, and then we eliminate the two assumptions here and here. So we get a full formal verification of the Kepler conjecture. So this is just a picture corresponding to the piece that was done inside the Isabel system. This is one of the computer programs. One part of the proof is to so first you reduce it from a problem about packings of all of space into packings in finite regions, and you create a graph where the centers of, where the vertices of the graph correspond to centers of spheres, and you connect the vertices by an edge if the centers of the spheres are sufficiently close together. We get a cutoff, and we get a graph that way. We can show that it's always a planar graph. And we write down properties that any potential counterexample would have to have. So what combinatorial properties would a counterexample have to have? And then we classify all of those graphs by computer. So that's one of the main computer parts of the proof. There are about 18,000 graphs that come up as part of the proof. And here are just a few that give us the most trouble. And then once we have an explicit classification of the graphs, we have a nonlinear optimization problem for each graph of showing that some density measure is less than this number pi over root 18. And for this, it's a nonlinear optimization problem that we do. It's called a linear relaxation of a nonlinear optimization problem. So we get linear programs. And then there's something like, 25,000 linear programs that we run that each involve maybe a few hundred variables, a few thousand constraints. And again, Soloviev made this part of his thesis, but he was able to get this linear programming to work very fast using dual certificates inside the formal proof system. And so all the different great pieces of computer code have been formalized. This is just a bit about the auditing process. The non-linear inequalities were double-checked at Radboud University. They got identical results, so that was I mean, with large computer calculations, there's always potential that you may have soft errors or something that flip a bit someplace. But we tried it twice and got identical results. And Mark Adams, one of the team members, I mentioned in connection with the self-verification of whole light, that you can export code from whole light into other systems. Mark Adams took the proof in whole light and exported it to whole zero and reran the entire proof from this other system as well. And so now the formal proof has been checked in 2 different proof systems.
So Tom, in terms of time effort, how much does it take for this kind of moving from whole light to whole zero and doing the same thing again?
I mean, it's an automated process, so he's able to replay things, I think, in just a couple of hours as the other system. So I skipped a slide. There's one proof that he had a little difficulty in exporting that we had to rewrite a little bit because it was producing such a big proof term, but other than that, everything went smoothly. So I was able to give, using the technology that came out of the simplifications of the proof, I was able to prove a couple of other results in discrete geometry that I won't go into. This project makes available certain resources, like this nonlinear inequality tool is a general tool that can be used by anybody who needs to prove nonlinear inequalities inside a formal proof system. And the same for the linear programming. Anybody who wants to formally verify linear programs can use this tool as part of other formal proofs. We have fairly significant libraries now. We have metric spaces, topological spaces, various combinatorial results about polyhedra, and so forth. And these libraries can be reused by anybody who has an interest. And then let me just say, what other things have been done with this project? So various people have become involved. So we've got a Google page project that's moving to GitHub. Anybody can download the code and do anything they want with it. So one thing is we've got this book giving text proof, and now we have a formalization of all of that. So there have been some interesting machine learning projects, for instance, where you want computers to try to learn how to increase automation of proofs. And these proof scripts in our project can be used for the data that gets fed into these machine learning systems to help out with automation and so forth. So I'll stop here. Thank you very much.
Any questions?
So you have in mind another problem to attack. Do it again.
You know, the Kepler conjecture started out as a small hobby. And it grew out of proportion. I tell people I only work on easy problems. There's some truth to it, because easy problems are already too much. So I don't have any big ambitions.
How much time would you have saved if the legacy of your project, as you just described, were available at the beginning? This gives me an estimate of how much time will be saved on the next project.
If I had all of the libraries.
If you had all the libraries to start with,
good time. So John Harrison contributed to some very substantial libraries. He contributed to multivariate calculus libraries and the library for polyhedra. I'd say at least half of the project goes into development of the library.
It's not the same in the Cell 4 project, at least at one stage in its development. So the next project should be twice as easy.
I think Gautier said that with the Feit-Thompson theorem, you take that as a 6-year project, the first 4 years went into the libraries, the last 2 years went into the Feit-Thompson.
The referees for Hales had said they were quite happy to trust a sort of non-linear inequalities proof, not a formal proof, but it's a sort of program that solved non-linear inequalities. But the thing that bothered them was just that a 300-page paper is very hard to read and feel 100% confident that you have to miss a mistake or something. If all they wanted to do was satisfy them about a 300-page paper, and they trusted you on the non-linear inequality, but that made the whole thing much easier. Sounded as though what you're saying it would, but or is that not your objective? To persuade the referee to come down?
So if I'm trying to estimate how much of the effort went into the computer parts of the proof. So there are actually 3 PhD theses that were devoted to the nonlinear inequality part of the proof. So I would say at least a third of the project went to the computer parts of the proof.
You mentioned you use both Isabel and Paul to go for amongst other systems. Why did you select Paul
So I made the decision before I knew much about proof assistance. And I asked Frank Biedike's advice. It came down to a decision between Koch and whole light for me. Eventually I picked whole light because it had fairly substantial libraries about real analysis.
For light, is there any limitation? I mean, is there any proof that that mathematician can prove by hand, but proof automation can't at the moment?
Well, whole light is a fairly weak axiomatic system, so I think once you start doing certain things with category theory, it would be quite difficult to formalize inside whole light.
Thank you.
Just to use Roger's frameworks, you believe now more mathematicians believe it's true? Or it is?
Well, like I say, my motivation was more to cut the referees out of the process than to convince the referees. And, you know, I always quote the statements from the referees about their doubt, but I mean, of course there was my own doubt about the code. Sam Ferguson was asked at this seminar that was presented to the referees how likely he thought it was that there was an error somewhere in the code, and he said he was 100% convinced there were errors in the code. And, many hundreds of small errors were found and corrected in the process of doing this formalization project. So I'm finally at rest. And that's all I care about.
Yeah, going back to the same point, and the point that you made about the fact that even if we trust the proof checkers, we still need to check that the definitions have been faithfully transcribed. Aren't we moving in that sense to a situation where the reviewer will have to check, not the code necessarily, but these definitions, and the reviewers in general won't do that, right? So have we, in your opinion, progressed from the previous state where the code wouldn't be checked to one that the definitions aren't?
Well, there are many orders of magnitude of difference between what you have to do now and what you had to do before. The definitions can be checked in an hour. And it would have taken a very long time to check the original proof of the Kepler conjecture end to end. And the rest, after you check the definitions, and there are certain other things you need to check, like you need to make sure that no new axioms have been added to the system, and you make sure that no malicious hacking was done to the system. Those are all things that can be done by any experienced user of the proof system. You don't even need to be a mathematician to check these other things, just somebody who has the right technical training to do this.
Yeah, one last question.
When you read and try to understand the proof in mathematics, which you can, for example, fit on one page, once you understand the proof, or if you prove something by yourself, there's a very clear satisfaction that occurs in your mind. And I'm just wondering when of course, you have a proof that runs over 300 pages or maybe how many hours it is done, whether that satisfaction is lost. Even if you believe that the system has corrected and verified all the chains, is there any comparable feeling?
I don't know. I get more satisfaction from a 300-page proof than a one-page proof. I depend on your own preferences.
But can you say a single point when you suddenly became satisfied? Maybe not.
Okay, thank you very much.
And as yesterday, we will have lunch next door.